So for this, what I want is, I want a style of galaxy that we're going to create here that is applicable for 4X gaming. Stellaris, Master of Orion, or Aurora 4X, which is excellent and exquisite, and that's like almost a little bit more the inspiration that I'm going in here. The idea being, at any given time, we can be looking at a solar system. Perhaps we could, pop out to a galactic map. We may not implement the galactic map here, but mostly it's about tracking the other stuff. In particular, I would like to go with semi-realistic distances in our galaxy. The idea that, I don't know what the distance from the Earth to the Sun is. I know that Pluto is like 4 billion kilometers away, and I want to be able to track sort of those units in a slightly more realistic way, but still have it look kind of cool. So we'll see how that goes. When's the tutorial for programming Skynet coming? Dibron, thank you very much for the resub. And yeah, I'm using the free version of Unity over here. You can also, get a professional version if you want, which mostly just gets rid of some extra logos in there at this point. It's amazing the features that have been included in Unity free. I actually have a code for the professional version, but there's no reason for me to use it. I got it as a bonus for something. What was it? Oh, it's because I've got the dev kit for the Oculus Rift. They sent me a key for the pro version of Unity, but I'm like, who needs that? Not me. All right. Good. Use light years, minutes, seconds. Could be. I think we're actually going to track things in meters. Because why not? That's because I want to address some of those units over here. All right, let's get ourselves started here. So there's going to be, like we've done before, we're going to try to separate out the data layer from the sort of presentation layer, right? If you've done any sort of application development or web application development, there's that model view controller sort of like separation. The idea that the model is where all your data is, and that is unique from your view layer. And the real good reason for doing that in here is because if we were to just spawn one game object, in Unity for every star and planet in a galaxy that could have billions, well, that would just explode your computer. There's no way to track that many game objects, to try to render them on screen, to do any of that nonsense. It's just not feasible. So instead, we are going to have non-game objects, but just regular objects and instances of classes to represent our data. And then, based on what solar system we're looking at any given point, we will then create game objects and sprite renderers, or mesh renderers, if you want to do it in 3D, to represent that data. So we're going to keep that sort of separation. That's one of the reasons also that the code we're going to write is going to be completely applicable if you want to go 2D or 3D. You can choose a variety of different ways to represent your galaxy visually while keeping the same sort of data back end. So what we're going to do is we're going to get started on the base data classes, which I will put in a folder called, I don't know, scripts models, I guess. I don't want to confuse things with 3D models, but I do want to have the idea that we're going to separate out the models, which is the data kind of thing. And I want to have a script for our galaxy. Then I want to have something like a galaxy is going to be full of, I guess, solar systems. So we're going to have a solar system. And then in that, we're going to have, well, then it gets kind of interesting. Do you want a class to represent the sun? And I guess so, or the star. So we'll say that. Right, in our implementation, we're just going to have solar systems have a single star, but you could consider binary systems perhaps. Then we're going to have, like, planets. Now, what's the difference between, say, a planet and a moon? Nothing. I mean, a moon is basically just something that orbits a planet, but in a very real way, there's no difference between the two. So instead of having class for planet, I'm going to call it orbital. An orbital is just something that orbits something else. For a planet, it's going to be orbiting the star. For a moon, it's going to be orbiting a planet. Asteroids are just orbitals as well. They're just tinier. That's really, there's no real difference between them, but that's it. So that's going to be the sort of idea. We have a galaxy that contains many solar systems. A solar system is going to contain, for our purposes, I will go with just a single sun, a single star rather, and then the star has orbitals around it, and those orbitals could have even more orbitals. And in a way, and I don't know if there's any actual example of this, you could have orbitals of orbitals of orbitals. Could you have a planet with a moon that has submoons? Well, I guess you could have artificial satellites, if nothing else, right? You can imagine that. If we put a satellite in orbit around the moon, then that would be an example of a big chain of stuff. Stars orbit the center of the galaxy. Yeah, so our solar system has a position as well, right? We have our galaxy, And our solar system is going to have some sort of position without that galaxy. So in a very real sense, is a solar system also not an orbital? Well, sure, why not? And in the case of a binary star system, the stars themselves, sometimes you have a big star and a little one, and one orbits the other, but a lot of times they sort of orbit sort of a common midpoint that's kind of hard to calculate. So can we just generalize everything to say that they're all orbitals? For our purpose, that is entirely what we're going to do. That is entirely what we're going to do to start off with. Boom. Orbital is going to be everything in our universe. And then, you know, or space body, space object, I guess we could call it. Everything orbits something else. And then what we can do is we could always subclass this later on. So that's going to be our base. It's going to be a good start. Then we'll build up from there and we'll see what happens. Who knows where this will lead us? So let's go and open both the galaxy and orbital. Now, these are not going to be derived from mono behavior. They're going to be standalone classes like this. And we're going to have our orbital over here, which I have to rename the class to orbital. Boom, like that. Now, one thing you could do, instead of having sort of everything be orbital, you could have orbital be like an interface. You could have all kinds of different things, and we might build up with using an interface as opposed to a base class. We'll just see where things lead us. So let's figure out the basic statistics of an orbital. Something that is an orbital must clearly have an orbital that is its parent. And I'm going to go ahead and just make this a public for now. Maybe, you know, maybe we want to change access levels later on. Maybe we're going to convert this into some property that's got a, you know, a property that's got getter and setter instead of a field. I mean, this is exactly the same as saying this, right? Whether it is a public field or a public property with just a getter and setter like this that's anonymous, 100% equivalent right now. So for the sake of not typing as many letters, we're going to do this. Next up, what do we have? Well, here's where it gets a little bit interesting. Something that orbits, public, has a distance, right? It has an orbital distance. Do we just call it distance? Orbital distance? We're going to go with round orbits, by the way. Just like in most 4X games, we're not going to care about the fact that things are actually ellipticals, where you would have a periapsis and apoapsis for the closest thing. We're going to assume a circular orbit. So we're going to say, yeah, radius, yeah, orbital distance. I like orbital distance. Let's make it super clear. We're going to have some sort of value called orbital distance. And then we get the first interesting question of here. What kind of type? What should our type be here? Now, it's worth noting at some point, we need to be able to get an X, Y, and maybe Z coordinate for our location for the purpose of rendering the orbital on screen. Spelling is hard. Right? At some point we need that. And in particular, what we actually are going to have, we're going to have some sort of public vector 3 called position. And it's going to be some sort of getter like this. To do. Convert our orbit info into a vector that we can use to render something as a Unity game object, right? So right now, what I'm just going to do is return like the 0 vector just as a dummy placeholder here. But at some point we want that. But I don't want to track my planet as a vector 2 or vector 3, because that's not really the best way to describe something that that is an orbit around something else. Maybe a spaceship could potentially be described as a vector in space, as has some location. But a planetoid really is best described as a distance from the parent and a current angle around the parent body. So a vector, the x, y, and z coordinates are floating point numbers. In fact, in Unity, they're specifically maintained as a float. And a float can have decimal points. and has a certain maximum precision. After you get a certain size in a float, so let's say this was a float, right? Let's say this was a float, which is fine, which is a way of doing it. Internally, floats are represented basically like a scientific notation, i.e. something, god damn, I can't spell today. So, or e.g., something like, this is 2.ba times 10 to the 6th power, or something like that, is basically how floats work. They have a certain amount of bits internally, and actually they can shift around semi-dynamically between the sort of value part and the exponent part, which is kind of a cool way of doing it. So they have, like, they can represent incredibly large numbers and incredibly small numbers, but because they have a certain limited amount of space for this, and they use a little bit of space for this, the precision is limited by basically how much space you've got over here. So it's very easy, for example, for a float to represent something like, you know, some number here with a bunch of zeros. That's easy for a float to represent. But it is very hard for a float to represent something like this. This 1 is going to get lost, which is perfectly fine in many situations. And if we use a double precision float instead of a single precision float, then we get, well, more precision. Now, this works both for very large numbers and also for very small numbers. There's sort of limits there, but it's great. And it's actually perfect for a normal vector 3 representation of putting things around. But we might want to... The problem with floats is that as you work with them, you can actually encounter a little bit of drift because of this loss of precision. A great example of it is, this was a problem in Minecraft. In Minecraft, the position of everything in the world was handled by floating point numbers because, of course, you can move, there's whole blocks, but as a character, you move, you know, a little bit at a time. So assume that each block is, you know, 1, 2, 3, 4. Well, your character can be at like 1.57 as you sort of slowly walk across the surface in Minecraft. Well, when you got really far away from the origin in Minecraft, what could happen is you'd actually get this weird floating point drift. This is also one of the reasons why in Kerbal Space Program, when you plan orbital maneuvers, at least before 1.2, sometimes the orbital maneuver would like shimmer and shake. Hey, we got a first tip of the day. Shimmer and shake. And a lot of that was because of floating point inaccuracy. So what I'd like to do is I would like to maintain our planet's actual representation via integer type numbers. So I got a tip in from the Shoob. Hey! The Shoob says, thanks for another programming stream. Have fun. Well, thank you very much. I am having a lot of fun. Hopefully you guys are enjoying it too. So what I would like to do is, instead of having things as a floating point number, is have things as an integer representation, which doesn't allow for decimal points or anything like that, but otherwise is completely 100% precise. So imagine that we tracked our orbital distance as an integer. So integers have whole numbers, 0, 1, 2, 3, 4, 5. The problem with integers, as opposed to floats, is integers really have a maximum number they can represent. Technically, floats do as well, but it's insanely high. Whereas integers, because their whole number of bits, have a maximum amount. And it depends very much on whether you're using 16 bits, 32-bit, or 64-bit numbers to represent them internally. When I grew up being a programmer, the limits of an int, I think, was normally 16 bits. And you could have a long integer, which used all 32 bits. But even in this case, a long integer, which is actually the normal int nowadays. And if you really want to be specific, in C#, if you're using system, then instead of using just the int keyword, you could be very specific and say int 32. But unless I got it wrong, in C#, int means the 32-bit integer. Now, how big of a number can you get here? The answer to that is because a 32-bit system can hold about 4 billion values. This is signed, which means it goes from negative 2 billion to positive 2 billion. You can have it be unsigned, so you could go uint like this, or you can literally just type uint, or you can type unsigned int. There we go. Either way, then, actually, I might be wrong about the unsigned part. Okay, yeah, it looks like I'm wrong. Sorry, too much C, C++ kind of stuff. Uint. An unsigned int does not allow you to have negative numbers, only positive, so this would go from 0 to 4 billion. The problem is this. How big of a number do we need to represent in our space system? Well, for example, Pluto is about 4 billion. That's 4,00,00,00 kilometers from the sun. Which means if orbital distance represented kilometers, that means the largest value of this just barely sneaks in the distance to Pluto. But of course, there are many things beyond Pluto, which are then too far away. Also, are kilometers precise enough? Well, for lots of things, maybe. What's interesting is, depending on the kind of game you might make, you may actually want precision down to the meter. One of the interesting things about Aurora 4X is that it has this incredible sense of scale, and it can process things as ticks as small as, I think, 5 seconds, but it can sub-tick even like 1 second at a time, at which point you're talking about things that may not move a full kilometer on every tick. So you might want to represent your solar system at a meter precision, which, all right, is maybe insanely insane, but isn't necessarily impossible. So what's the solution there? Well, we can choose different representations. One of the things, if you do use floating point numbers, right? So the possibility number one, you could represent distance as AU. AU is an astronomical unit where 1 AU is the average distance from sun to Earth, right? So that would be a good representation for a float. It's great if all you're doing is representing planets, but if you're representing little ships going around the solar system that might get a lot closer to each other, then this level of distance might be really bad. This is really good if you're just concerned with planets, big distances involved. It's great. Alternatively, you might want something like public float int, or more accurately, why not unsigned int? Because there's no such thing as a negative number from the sun. There's just a positive number from the sun. We're going to have an angle component as well. Hell, you can already think of that. This would be a float. Something, well, probably a float. Public float angle. Angle around the parent in radians. It'll make our life easier if it's in radians. So you'll have that. So then you can combine this with, yeah, so you combine these two for that. You could have an unsigned integer, so it's a positive number of orbital distance, again. That maybe is something like, maybe in kilometers, as long as nothing is more than 4.4 billion from the sun, which is the distance of Pluto. Unless I've got it wrong. I should be taking a look at the check over here. Seems all right. Well, the orbital speed, yeah, we'll definitely need something like that. I'm going to say, while this may be overkill, why don't we just say public... Oh, I have float in there twice. Why don't we just use a 64-bit number? So in C#, if you define a long integer, it uses the next level up in terms of bits. For me, growing up in the early days in C, that meant like a long was a 32-bit number, but that's no longer the case anymore. If you're worried about having it be explicit, go ahead and be explicit. Let's say we want to make sure it's a 64-bit integer, which again, in C# is the same as saying long. Specifically, because we don't need negative numbers, we can have it be an unsigned integer. And again, this is the same as saying u long. So now if we have orbital distance, this in meters, maybe overkill precision, maybe not. Now, the only gotcha with this is technically 64-bit math can take a little bit longer than 32-bit math, but probably not. If you don't actually have a 64-bit processor, then that might be a little bit slower, but C# will fake it. The other thing is if you don't actually have a 32-bit environment, then if you're doing multi-threaded stuff, this is not an atomic operation, and if any of those words didn't make sense to you, don't worry about it. That's a whole nother thing. So there's the one caveat is if you're in a multi-threaded environment, not in a 32-bit environment, or if you're making a multi-threaded program and you're running on a 32-bit system, then this is not atomic, so you have to make sure to do a proper lock around it. Irrelevance. Okay, so this means we can track our distance in meters. Cool, fun. What's the maximum number of this? Max value is, I have that open. Where? It's a giant number. It's awesome. Is that... it's going to do the thing where copy and paste doesn't work. Thank you very much. Is this. And the distance from Pluto is... Pluto is... stop doing that. It's 4 billion kilometers. But if we're converting this to meters, we add 3 more zeros, which means we've got this. So clearly, we have a number range that can handle. So this is in trillions of meters, whatever comes after trillions, and whatever comes after that. So this would be what? Quadrillion and quintillion? We can handle some pretty damn big numbers. All right. Anyway, talked a lot about the number types, which is worth the discussion, actually, because we haven't really dealt with that before. But let's actually move on and make some fun. So we've got this angle, which can probably be held as a floating point number perfectly fine. Maybe, I don't know. It can't really be mapped as an integer type. We might want to use a double precision if we're really being paranoid about this kind of stuff like that. So this is the current angle. This is our current distance. And we probably want something like, I don't know. We really don't need a 64-bit number for this. But let's, you know what? Let's standardize on it or some damn thing. I don't care. How about something like time to orbit? How long does it take us to get around our parent body? And maybe we'll have this be in seconds, since apparently we're going insane with our precision. You can always scale this back later on. That's fine, but you know, let's do that. How long does it take to get around? So if we wanted to make the Earth, right? Let's make a little dummy function here, just as an example. Make Earth. So we would start, let's say we start at an angle of 0. That's fine. Which presumably is like north of the sun for some value. Orbital distance. Earth orbital distance. 940 million kilometers is an average. So we say 940,000 million kilometers. Million kilometers. Or 940 billion meters. So that's our orbital distance. Our time to orbit is, well, in seconds, 365 days times 24 hours times 60 minutes times 60 seconds. There you go. That's our time to orbit. So this is how we would describe the Earth. Well, Kepler's third law gives orbital period from orbital distance. It's redundant. You're right. That's true. That's true. That's interesting. To do. Kepler's third law? Let's just write them in for now. Okay, that's actually interesting. We may go and revisit that. All right, so we've got this. So we could make an Earth, and it's a pretty sweet Earth. So how do we get our actual position if we want to draw it on the screen? Well, that's fine. What we can do, so we'll make a vector 3 called pause, new vector 3. Well, I guess I could just return it. That's going to be okay. Yeah, let's just do that. So instead of returning vector 0, we'll return a new vector 3. Which needs an X, a Y, and a Z. Now, for our purposes, so let's just do 0, 0, 0 for a second here. Z is locked to 0, but consider adding inclination if in 3D. Right? So we're going to assume, just like we're assuming that everything is perfectly circular, we're going to assume that everything is perfectly planar as well, as opposed to being shifted in different ways for our purposes. But it's very easy to add an inclination angle, or just to add, you know, more realistic variables that we have to worry about. So what are we doing here? Well, our distance along X that's how far it travels around the sun, not the distance from it. Oh, did I? When I Googled Earth orbital distance, Oh, you're right. And Google very helpfully gave me the circumference as opposed to the distance. The distance is about 150 kilometers. Thank you very much. All right, so we got that. So, get my calculator over here so that I can confirm some things before I lie to you. How do you get the scientific number over here? So the sine of 0 is 0, right? Yes, good. Okay, so if we assume, whatever coordinate system we want for the angle, but if we assume that an angle of 0 is sort of straight north, then the x component is going to be the sine of that angle, right? So mathf dot sine takes a floating point number in radians. So it takes an angle in radians. So we've got an angle in radians and returns the sine of that, obviously. So if we're going straight north or straight south, this will return a 0, which is great. So we're going to take our orbital distance and multiply it by that. So when we're straight north or straight south, this will return 0. If we're east or west, this will return some positive or negative number. So that's going to be fine. And then for the y component, we're going to do the cosine of exactly the same thing. Now, you are likely going to be reading this quite frequently, right? This position when we're updating things. Consider whether or not we should be saving vector 3 in a private variable whenever we update our angle, or if it's no slower to just calculate on demand like this. Depending on how often you ask for an orbital position, if you ask for this much more often than you change the angle, then you're going to want to save the vector 3 in a private variable and just do that. If you end up asking for position about as often as you change the angle, then this is going to be the same in terms of processing speed, and actually saves you a little bit of memory because you don't have to save it. Do some benchmarking. It's probably not a big deal one way or another, but these sorts of math operations are technically could be a little bit slow if you're running these a million times per second. So keep that sort of thing in mind. All right, so we've got that. Hopefully I've done the math okay. Who knows? All right. So one question is, what is our current angle? So right now I'm forcing the angle to be 0. But is that correct? No, what we'd like to know is really we need to know the angle at a certain time. Like we need this thing to orbit around, right? So we need some sort of update routine for this with a delta time. So this is just an example, but we need some sort of public void update that takes a float delta time, very, 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 very similar to how you'd work with most things in Unity, right? So advance our angle by the correct amount of time. Now, what we could do is some sort of like angle plus equals whatever. But what if actually instead of delta time, because this is 100% deterministic. One thing that can happen here, if we keep changing the angle by some amount, and we keep getting these little tiny delta times at a certain amount, things can sometimes drift because of the inaccuracy of floating point numbers. What if instead of this, we said our update requires time since start, time since the Big Bang, because there's no reason we can't figure out our angle based on something like that, because we know our speed, right? We know how many orbits we've gotten around. I'm not going to save this, but let's say num orbits is simply equal to the time since start divided by the time to orbit. Time to orbit is something we're setting right now, but this itself could be calculated, right? So that's the number of orbits, is this, which means that our current angle is equal to num orbits times a full circle in radians is 2 times pi, right? Pretty sure. Hold on. I'm like, there's that one little moment where you're like, oh, I'm having the dumb. Because pi is 180 degrees. 2 pi radians. Yes, good. Get those little moments. Math is hard when you're doing it live. Thank you to all our August patrons, i.e. people who pledged in August and who are supporting videos from September through to early October. And especially these Mic Check supporters. We got Ole Peter Talgo, Adam Conway, Drazion, Jan Torivel, Adjective, Michael McClintock, Aaron Toyson, Craig Mortel, Julian Auger-Lafont, Marius Fieldvold, Speedy Savant, Steven Stager, Valiant Cake Fiend, Wes Oldenboiving, Jason Yanity, Kale the Quick, Neil Blakey Milner, and Yukofin, and everyone who's watched, shared, favorited, and subscribed. Thanks for watching. See you next time.